Hello everyone, welcome to the CPU scheduling chapter. So this is a reminder of the idea that with multiprogramming we are aiming to maximize the CPU utilization. And so the processes in the system are actually alternating between two cycles. CPU cycle during which all the processing on the CPU takes place, and the I/O cycle where all the input-output requests are handled, and processes keep going back and forth between processing time or CPU burst time and input-output requests. So remember that processes are different in terms of the duration of their burst cycle and the frequency of these cycles. For example, remember we talked about the let me activate the pen here. Remember we talked about two types of processes: CPU bounded processes and I/O bound processes, right? And we said that CPU bound processes are those processes that require CPU time most of the time. They have very infrequent requests to input or output data. Whereas when we talk about I/O bound processes, here these processes, they spend most of their lifetime just requesting, reading or writing data. And so some processes would have long burst time, right? That's in this area right here, but the frequency would be really low. So these processes, they tend to require to stay running on the CPU for extended time periods, so they don't have frequent requests. Whereas for I/O bound processes, they do not have long burst times. They have very short burst times, but frequent ones, right? So they need to run on the CPU for a small amount of time and then do an I/O request, an input or an output, and then go back again, make another request to run on the CPU, and so on. So the frequency is higher when it comes to I/O bound processes versus CPU bound. And so also remember we talked about the CPU scheduler, which is that module responsible for applying the CPU scheduling algorithms. So it is the job of the scheduler to decide among the processes currently waiting in the queue which process should go next to run on the CPU, right? So there's always this list of waiting processes, so we keep track of their PCBs. And then, depending on which scheduling algorithm the scheduler is currently running, it would choose the process to run next on the CPU. Now, scheduling algorithms come in two types, preemptive and non-preemptive. With the non-preemptive version, once a process is chosen to run on the CPU, we are not allowed to interrupt that process unless the process itself voluntarily yields the CPU, either because it has terminated or because it requires an I/O operation, right? So you can see here that process P1 starts executing at time T1, and even though we have another process P2 who's waiting, we are not allowed to interrupt P1 until P1 is completely finished or yields voluntarily the CPU. Versus if we have a preemptive type of a scheduling algorithm, then in this case, we do have the ability, for multiple reasons, which we'll discover when we study these CPU scheduling algorithms, we do have the ability to actually interrupt process P1 before it finishes its requested burst time to run another process, and then we resume the execution of process P1 again later. So there are multiple reasons why would we do that based on priority, for example, if we are applying a priority-based scheduling algorithm, and other reasons as we will discover when we study the scheduling algorithms. And so in addition to the scheduler who is actually the component responsible on choosing the process who will run next based on the scheduling algorithm, the other module or component responsible for context switching is the dispatcher, right? So once the scheduler has chosen a process to run next, it is the job of the dispatcher to handle the context switching process, which we've talked about previously, which consists of saving the old state of the currently running process and the loading of the new state of the new process chosen by the scheduler. And this takes time. Remember, we talked about the latency, or the context switch time is also called the dispatch latency. Now, this one will vary from hardware to another, but it's pure overhead as we've described before. And so, as we will see, there's a variety of CPU scheduling algorithms, but all of them have the same common objectives, which is to maximize the CPU utilization, to maximize the throughput, which is the number of tasks or processes that we can complete per time unit, and also to minimize the waiting time, which is the time a process has been or has spent in the ready queue without processing, and also to minimize the turnaround time, which is the total time that a process has spent in the system since arrival all the way to departure. And so once we are comparing these scheduling algorithms, we will be comparing them in terms of these two criteria, the waiting time and the turnaround time, and we will see how we can calculate these two attributes. One last thing also for simplicity, we would assume that we only have one core in our system. Okay, it's not a multi-core or a multi-processor system, and we are only going to consider one CPU burst time of each process. So we know that processes will keep coming requesting CPU time, but for simplicity purposes, just to compare the algorithms, we will just study or compare the first CPU burst request.